See, that's going to be hard to pull off, right? Because Tim's going to hear that. I think we can make it happen. We'll get ahead, and then we'll do a...
Or we get far enough behind if there's no catching up.
It's a lost cause. We're done. So a couple things here. So another assumption that we make, so we were talking about this basic strand plan. I'm just going to do a quick little review. Another assumption that we make during our analysis calculations I didn't mention before, right? One of the things we mentioned was, our steel strain isn't going to change. It really is, right? You're going to apply a load to this, right? And then this thing is going to bend down. And so the bottom's going to go into tension. It's going to stretch that steel a little bit more. And since it stretches the steel a little bit more, the stress is going to go up. The other assumption that we make is that the forces from the pre-stressing are always acting horizontal. They're not necessarily, right? There is a vertical component to these things when we do a pattern on that. But when we do the actual calculations, when we actually calculate, this right here, we just assume that the pre-stressing force is acting horizontally, but it does have a vertical component, and we ignore the vertical component. There is a little bit later on when we do shear design, we will take into consideration that the vertical component, but for the most part, though, we just ignore it. We ignore that there's a vertical component, and we ignore that the horizontal component is slightly less. But also, these are definitely not drawn to scale, right? This is going to be, 30 feet across, and then up and down right here is only going to be like 16 inches. And so your EP is very small compared to how long it is. So these are very, very exaggerated, right? Now you guys are all super quiet, and now you're making me nervous. Right? You're talking a bunch, and now you're paying attention to me, and I was like, oh God.
Do you want us?
No, I don't. I see Gavin. It's interesting. I just had this like flush of like, oh my God, everybody's looking at me, and then I get that every once in a while. But stage fright. I do those stage fright. Yeah.
I did see a camel video yesterday pop up.
Listen, it's listening to us, right? It absolutely is.
Paint green camel video.
Yeah. That was a pretty funny exchange.
Alpacas, and they're definitely llamas.
Alpacas are definitely llamas?
No, the alpacas down the street are definitely llamas.
Are they really?
Their faces,
It
they're
says
definitely
on the
llamas.
sign, it does.
Oh, it does say on the sign llamas. That's another way to tell.
Step one.
Don't look for the exhibit sign.
That might be step one.
Listen, memory is hard.
Yeah.
It's
Okay.
hard.
All right, so then we talked briefly about this. This is where our big detour went last time. The sea lion method, right? And again, it's kind. I just opened.
You know where you can't hear construction noise?
At Specs. All right. Give us a sec. Right. So the point of this topic was just saying, like, look, in regular reinforced concrete, C and T are a fixed distance apart mostly, right? And then as you apply load, C gets bigger and T gets better, but then that moment arm stays the same. Whereas it's different over here in pre-stressing. You have this big pre-compression force to start things out. When you start out, they're lined up when there's no moment on it. And then as you start applying moment, then this FC starts changing, right? The moment arm changes and FC and FP remain constant. And then you can plot FC along the length of the structure, and then you can apply limits to it and stuff like that and see where it lands. And then the whole point of this is just to show you these mechanics and how they're kind of unique. And then also this discussion was, where this FC lines up. If it's above the neutral axis, that big FC is where all the compression is going to be, and over time that thing's going to creep. And if it creeps up at the top, it's going to sag down. If it creeps down at the bottom, it's going to creep up, which is just a weird, you think gravity, right? But it's going to cause things to sag down, like the corners of Cobley. And that's your constant load. This constant load's coming from the internal pre-stressing force. So that's a constant load that's always there, and then it'll creep up on us, which is weird. Okay, so then we were going to briefly discuss kerns. We talked about this last time. One, the definition of kern in mechanics stays the same. It has to do with zero tension. It shows up in geotech. It showed up in, where did you say?
Foundation.
So it was geotech stuff. Yeah, the kern definition. So we do have a kern here. You'll hear it thrown out on occasions if you're ever reading about pre-stressing. And then Stanton's notes uses it in the mechanics equations. But as we, like we discussed, and I just mentioned right now, it's associated with having zero stress at a certain point. And so we're going to look at this case. This is for the top. We're going to have zero stress at the top. Okay. So this is zero stress at the top. You can also do this for the bottom, but we're just going to do it for the top. Okay, and so what we do is we come to our equation. We're going to try to find where that happens, where we get zero stress at the top. So we go back to our equation, right? And our equation is this. At the top, it's going to be F2. F2 is equal to negative FP all over AC minus FP EP all over S2 plus M external divided by S2. Okay. And so again, we're trying to find this. We're this is the stress for this, and as you change S, it'll give you the different locations along this thing. But up at the top, oh my God, up at the top, I think he moves it every once in a while is what he's doing. Right, there he is. The other day I was in a meeting. I was at a Teams meeting, and I was in the middle of this Teams meeting for a research funder, and we're having this conversation. And there, no joke, I hear something. I look over to the right, and there's a guy's head, literally just looking at my window. He was just staring, like he was working on something. He was scraping stuff out of my window, and his head was just right there. And it's a pretty important meeting. And then one of the guys noticed. He's like, "What are you looking at?" It's like, "Oh, well, I'm looking next to my buddy here." And I like rotate the camera, and then the guy just like he waves from outside the window. Oh, that was pretty funny. How did this guy? Okay, so we're trying to find when this thing's equal to zero. So we set this equal to zero, right? Because that's what we want. And this is at the top, and so we're going to set that equal to zero, right? We're also going to do this for no external. This is solved for no external moment. So this current that we're talking about is for no external moment. Okay, so that M external is going to go to zero. And so what we're going to solve for is EP, right? We're going to solve for EP. And, this is equal to zero over on this side, right? And we're going to solve for EP. So FP could go, right? You just divide both sides by FP. Those will go away. And then we can kind of keep going with algebra here. 0 is equal to -1 over AC minus EP over S2. And then I could solve for EP. EP is equal to negative S2 all over AC. Right? And this, even though we're talking about F2, this is actually an upper limit, and we'll call this K1. Or lower limit. It's K1. It's the limit down at the bottom. So what this is this is the lower current. I call it lower limit. We'll call it lower limit. It is the max eccentricity of strands such that no tension in the top with no external moment. So that'll be a distance, right? That's a distance. And so that's going to be the lower limit. It's going to say the idea behind this is if I go below that limit, if my EP goes lower than that, then I'm going to get tension up at the top, right? And then the same thing could be done for the other side. You can find out the upper limit. So if my EP goes above the upper limit, then I'm going to end up with tension down at the bottom, right? And so you can just say, right, K2, we'll do it like a dot, dot, dot. I don't want to, it's the same derivation. It's just flip it around, dot, 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 right? K2. It's a little confusing because K1 has to do with tension at the top and K2 has to do with tension at the bottom, but it has to do with, you don't want to go too low because then it'll pop up, and you don't want to go too high or it's going to kind of pop down. So So K2 is equal to negative S1 over AC. Right? And this would be the opposite, right? This is upper limit, max eccentricity of strands, I mean basically the same thing, such that no tension at bottom under no. Right. And again, right, very similar to what you did in, right, it was in geotech, it had to do with a point that didn't have any tension in it, right? So it's like so it was very similar. A kern. This ties into the lingo that we were just talking about, right? It's like a word you don't hear very often, kern.
Is it always the center third for this?
Center third through this.
Third is the triangle centroid is at 1/3 of that bottom. So 0 at the top,
Yeah, 0 at the top.
and then the centroid of the triangle is 1/3.
Yeah, it'll be at a third here. Yeah.
Is
That's
that
where the
always case?
well, you're confusing me, Kern. Thomas, you're confusing me. I mean, it'll always be. I mean, the resultant will be at a third. I mean, are you saying that this ends up being at the third?
Yeah.
It is.
I think it's just for rectangular beams, but
Oh, I'm gonna have to think about this one.
okay.
I don't see the third, but it is the third. You're saying it is the third?
I think so.
I think it would be. I'm thinking about it. I'm not saying you're crazy. I'm not like looking at it going like this guy's crazy. I'm trying to think because S is going to be from the CG for rectangles, right?
Yeah.
Because that would have to be applied. Then this would just be H over 2. And AC is H times the width. It might be in there. So I'd have to spend a little bit of time. So it doesn't matter though, okay?
Okay.
Okay, this is. I mean, I do like you typing it, but I'd have to think about that a little bit more. I can't do that kind of math in my head, but I think you're on to something. Now, but we're not going to use it. That's right. We're not going to do it. The other place that it gets, and it's just, I just wanted to show that that's what this whole definition of Kern does. Stanton spends a bunch of time, Kira, the one person that's read it, he spends a lot of time talking about Kerns in there, right? And then the other thing he does is after he defines what a Kern is, he then substitutes him, and I mentioned this last time, into this, like, I love this equation, beautiful equation, right? Concentric pre-stressing, the effects of the eccentric pre-stressing, external moment, beautiful. But then he just violates it. And he says, let's just rearrange some stuff. And this is the process that he does. He just rearranges things, adds in this M external is FP times the distance in between EP and EC. This we actually showed, if you want to spend time on this. We showed in C-line. When we discussed C-line, we discussed this thing in there as well. Right? And then if you do that and do the substitutions and stuff, you can get that above equation down to this, right? And so it's in terms of kerns as opposed to in terms of other things. And the reason I don't like this, right, is because now the external moment isn't even in there. You've thrown in this EC that's floating around, and that EC you have to calculate from FP and EP and your external moment, and like it's dumb. It's stupid. Stanton's stupid. I don't know why he does it. He also does it in the article. Kira read it. It is on the sign convention. There's an article on the sign convention. He slips in these kerns in there as well for some reason. I took class from him, and I was like, they confused the hell out of me, and I was like, I'm not going to do it. But then I have to show you anyway. Because I had to do it. You have to see it at least. Okay. So then let's talk about design, right? All the stuff up until this point is just the analysis. We have an equation for analysis. We know that there's different load stages, but how do we go actually about designing these things? Okay, when you start out in a design, let's write down our knowns. Right? We're going to know the moments, right? We're going to know M totes, M live loads, right? It's got a little free. Write down all the stuff in dead loads, right? We're just gonna know the loads, right? Loads are known. Oh, I'm missing an N there. Loads. We're gonna know the span, right? The demands. We're gonna know the stuff. The spans, support conditions, right? And then the other thing we know, or at least we assume we know, is the material strengths. Those are kind of usually the things that you go into this, or we get to specify those things, right? We're going to specify what the concrete strength, or the support conditions, the spans, what our demand. I mean, basically what the demands are, right? And then what we don't know, are variables. Variables that can change is I don't know what the pre-stressing force is. Right? The required pre-stressing force. I'm going to come back to that one in a second. Okay, we don't know the shape. There's a bunch of different shapes out there, but we get to choose that. We get to choose what our shape of our structure is going to be, or our beam is going to be. Associated with the shape are its dimensions, right? Right, and all of the properties like AC. Is it a property? I don't know. I, the moment of inertia, I don't know. C1 and C2, right? Those are going to show up, right? And then the other big one is EP, right? Where is my pre-stressing at, right? So usually go into the designs like what we're going to do in class, though, right? I'm going to give you the total. Well, I'm going to give you M-totes. Right, I'm going to give you the live loads, the dead load breakdown, the spans, the support conditions, the material strengths. Those will all be given. I'll also give you the shape, right? But really, in a true design, right, you would have to come up with what the shape is and what AC is and what I is and C1 and C2, right? You would have to come up with those. But in this, for the sake of this class, right, I'm going to give you those things. And we'll even some of these design methods down below, like the design manual, you can look them up and then it'll tell you the shape based off the design manual. But we're going to start out with those things being known. So somehow if you want to reference to those are going to be known. But we're not going to know what our total pre-stressing force is and our EP. That's what we're going to be varying, is where is our pre-stressing at, and then how much pre-stressing do we need. Those are the things that we're going to design for. So a couple notes, like on your homework, and maybe, I'm sure all of you have done it. It's due today, by the way. Kyle hasn't started it. Who's done their homework? Nerds. Yeah. It was one of my funniest jokes ever. And maybe you were in on this class in dynamics. Somebody's calculator died, and then I was like, I'm sure someone in here has 2 calculators. So let's just ask if anybody. Does anybody have 2 calculators, right? And there's like 10 people raise their hands. Like, I got 2 calculators, and I'm like, nerd in front of everybody. It's pretty funny because they lent out the 2. Yeah, anyways. I thought it was really funny, but also probably not very nice. Here he is like donating their calculator to help someone else, and I'm calling him a nerd. But I mean, come on, who carries 2 calculators? Who carries 2 calculators here? Z, right? Like, but it's okay. So I keep telling them too, lean into it. Lean into it, guys, right? I see you are, so that's great. Just own it. What's that? You have 3? You do. Oh, 1 up to.
Making fun of someone for how they hold their pencil during.
Dude, that one was weird, man. Do you know that kid?
I knew someone sitting behind him.
He was holding his pencil like this in an exam. Did you see? He was holding it like.
What are you talking about?
Dude, and I was like, it was in the final, and I came over, and I was like, is everything okay? Like, are you okay? Because he's holding it with all his fingers, and then his buddies behind him just start erupting in laughter. They're like, what the hell? I ran into him afterwards. Like, after the class was done and stuff, I ran into him downtown. He's like, what are you making fun of my writing? I was like, well, but who holds their pencil like that? Who does, right? I don't know. He had no defense of it. So those of you that have not, see, I hate doing this, right? Because you did your homework here, but now I'm going to tell them something that you maybe struggled with before.
Yeah, I don't feel good about it.
Oh, I won't tell them. Sorry, guys.
Tell us.
No.
What?
No.
It'll help
Well,
too.
Yeah, it'll.
Okay, I mean, so here's the deal. what you got to be careful of, a couple of things. Signs. You got to be careful of your signs, right? Compression and tension, right? Compression's going to be negative. Tension's going to be positive. So when you're comparing limits, make sure you're comparing them right. So when you're checking your compression limits, you're going to get a negative number. You might get a negative number. And that's okay because you're comparing it to the negative limit, right? And then that negative limit has to be greater than the negative value has to be greater than the negative limit of the thing. So you got to be careful, right? And then again, S1 being positive down, S2 being negative up, and that'll lead you to that. And so you're going to get some negative values. So then I would also it's going to be tension, or usually when you design these things, usually what's going to happen is going to be tension at the bottom under service conditions is going to control, right? So what you do is you solve for the number of strands you need for that case. And then once you come up with the number of strands for that, then you come back and check to make sure it's okay with compression at the bottom under those conditions, and then make sure that then you go back to the initial conditions and make sure that it's okay under the initial conditions. Where you run into problems is if you try to solve for the number of strands that you need for each one of those load conditions, weird things happen. Right? There's like you're solving for different kinds of, like if you were like, oh, I'm gonna solve for the number of strands required for it to have compression failure at the bottom, right? If you do that, you get some weird number because it's very unlikely that compression at the bottom is going to control. And then you're actually finding a different limit. You're not finding the minimum number, you're finding like the maximum number. And so then you got to go in between it. It's easiest just to say, I'm solving. And then when you solve for the compression at the bottom, if you were to do it that way and the number of strands you need for compression at the bottom, you would have to put in the value as a negative number on the allowable on the side. You would have to do that. And otherwise you get really strange answers. So the easiest way to do, start out with tension at the bottom, then you get a number of strands, and then you look at compression at the top. Compression at the bottom, compression at the top under service conditions, and then you check the initial conditions afterwards. Technically, and if you didn't do this, that's okay. Technically, under initial conditions, where you're going to run into problems is at the ends. And I didn't say to do this, but really, what you would really do for tension at the top and compression at the bottom would be at the ends. Why would I care at the ends? Because that's where you have no self-weight. There is no self-weight moment there to cancel out your internal moments, and so that's where you would run into problems. Is actually over on the ends. I didn't say to do it. So if you didn't do the ends, that's fine. We're going to do that next time when we plot all of our stresses. The other thing to do is I keep throwing out this FP, right? The required FP that you need. Well, FP is just equal to your stress, FP, right, FPE times the area of the pre-stressing, right? And so just keep that in mind. That big FP is the pre-stressing stress. I give you this in the problem statement, right? FPE and FPI, I give you those. And then to get the capital FP, you multiply it by the AP. The AP is where your number of strands is going to be, is in that AP, right? You're going to have the area of one of your strands, which you have to get out of the table. You can't just do pi d squared over 4. You have to get it out of that table I gave you. And then that'll give you that area of one strand, and you multiply it by the number of strands, and it gives you that, right? So then usually I think what I did is I solved for the AP that I needed, and then solved for how many strands would give me that AP, and then I got 9. What did you get?
I got 10.
See, you got 10.
Yeah,
I got
also
10,
got
he
10.
got 10, he got
Well,
10.
the 10's the answer then. I trust you.
It went out to like 9.38.
Yeah, see, I got 8.08. I think you were okay. Connor, I'm gonna trust you. And mostly Kira, but I trust Kira. But I'll trust you by association. I'm gonna trust you by association to Kira and Sean.
I'm just not going to turn it over.
So there's a chance that I made an error in my calculations. Unlikely, but I probably did.
Even
So in that case, you should delay the
We-
due date.
Yeah.
until you have the solution.
So we went through everything though, and all my numbers right. Maybe it's the calcs.
I'm checking, right? I'm looking at mine right now.
On MathCAD,
Yeah.
and then you get 10. So you get 10. 10's the answer.
I'm getting,
Yeah. What did you get? No, you did it. You got 10. Yeah, 10's the answer then. Did I say 9 earlier? I meant 10. I meant 10. I wasn't finished. 9 plus 1 is what I was going to say. 9 plus 1 was the answer to this. Okay. So just that should set you up. You're fine. You're fine. You can do it.
Yeah,
Val, you
just
can
had
write
it.
down 9.
Just write down. Just write down 9.
After that, so I'll show you.
Okay. So then again, what are we after? We're after the total pre-stressing force, right? And the where we can place these things at. And actually, to be honest, mostly where we can place it. Because I think our first homework assignment, I even tell you what our pre-stressing force is, or at least how many strands we have. And then you have to tell me where it is that you can place it. So where's the EP going to be? Okay? And so one way we could do this is direct solve is what this is called. And this is one of my favorite. Guess and check. Okay? That's my favorite design methods out there. Because what we're going to do is you're going to have either an Excel spreadsheet or a MATLAB or a MathCAD or something like that. You're going to have a plot of your stresses, and you can see to make sure that they're okay in all the locations, right? And then if they're not okay, you change it, right? And the way it's set up now with computers, right, or Excel or MATLAB, you just go in and say, oh, I thought my EP was going to this. I'm going to change the EP, and then now is it okay? I'm going to change it again. Now is it okay? Now is it okay? And see if it works, right?
Can you write macros to do this?
You probably can. You're damn right. I can't. ChatGPT can. I can explain it to do it. Yeah. And it could do that. Or you just do like a guess and check, right? But also keep in mind, this is something we struggle with all the time as professors. Well, there's programs that do all this shit, right? Like, there's like I'm going to teach you how to do it by hand, which is important, right? Because you have to understand fundamentally what's happening behind the scenes. But also keep in mind, like if you're in the real world, like you could do a macro or something, or you could just put it in EnterCalc or the equivalent for pre-stressing and then let it handle. But you got to make sure you're using those things correctly, and then making you struggle through it yourself first will make you appreciate that. You appreciate that? No. Like back in Structures 1, where I'm like having you guys all make these big matrices and then partition them and then invert them and stuff. The whole time I'm just giggling like, you'll never do this. But again, I think it's important for you to see, because that's like, remember when we did Structures 1, I could show you what my answers were from my MATLAB program, and they were exactly the same as what VA was giving you. And so behind the scenes, VA is doing exactly the same thing. It is making the matrices, it's partitioning them, it's solving them, and it's to the thousandths. I still can't say it. Thousand. Can you say it? Thousands. Thousands. What is it again, John?
Thousandth.
See, I did it.
Thousands?
See, it's hard. Thousandths. Thousandths. How do you pronounce this word? You have to come up and whisper it to me. That's going to be on the exam. Come up and whisper. How do you pronounce this word?
Let me get this straight. One of our exams is going to be matching animals.
Oh, my God. I tried to get ChatGPT to make me that problem. You should see that it let me down so hard. Let me see. I was so mad at it. Oh my God. Let's see if I got it. I saved it. I gotta find it here.
I think we should take a vote on if the final should just be all the random stuff with the humanoid and all those.
Yeah. Good.
Stressed.
Sounds
I'm
good.
so mad.
We're only 3 weeks in.
We're only 3 weeks in and there's an entire exam for random stuff.
I'm so mad at it. I still don't. I was like, you make me this, and I told it the animals to use. And look at this shit. Look at this shit that it gave me. Come on.
Yeah, it is pretty.
Like, I mean, you son of a bitch. Right? Look what it did. I think I see the camel. I think that, right? I think this is the camel. There's the hump, right? This is either the llama or the alpaca. I can't tell.
I think
between those.
shorter ears.
These are the seals and the sea lions right there, right? Because they don't have legs.
The top one's a seal.
Do you really know?
Yeah, it looks like a seal. It's like long. And
Long string.
See, I think it actually incorporated it, but he made its own. It made its own drawings, and so I went back and I was like, listen. That you could do better, and then it was running into problems. It was running, we went back and forth a lot, and I was turning on the most powerful version I had, and it took like 10 minutes, and what it was running into problems with is copyrights on images. Like it went and found the images, but it refused to like steal their images and put it in my document. So it gave me directions on how I could steal them, and then put it in as well. But this, I was like, you son of a bitch, you son of a bitch. But I think it got it.
I can't wait. You're gonna put that on the exam.
I really should. I should put it in this format right here.
It's like the llama and the alpaca.
Is it like turtle and tortoise?
Do you know the difference between the?
Yeah, the bottom middle is an alpaca and the top middle is the llama.
Why?
What?
Because the bottom one's fluffy.
Oh, that is what it is.
What other animals do you want?
Well, there was a wolf and a coyote. So one of these, the upper left.
I think upper left is
Did it give you a
middle left is
What's
coyote.
the thing coming off?
Wolf, coyote, and I think there was an extra.
Which side do you do bears, Al?
Oh, I did do bears. I did black bears and grizzly bears.
Okay, so bottom
no.
right is
Bottom
the
left,
grizzly,
bottom right.
bottom left is the black bear.
This is a grizzly because the hump on the back.
Yeah.
Yeah.
And then what's the?
Top
And then this is the
one.
black bear.
Yeah.
And then these are the wolf and coyote.
Top
Yeah.
one's
Yeah.
the coyote, middle
Isn't
left
that-
is the
The
wolf.
top one's
Why?
the wolf because the tail's out straight.
Yeah.
Oh.
It also looks slightly bigger.
That's maybe that is going in just like that, straight in. What do you think, Will? By the way, Will, I heard you've graduated to Will 2.
Yes.
You moved up. You're not Will 3 anymore. You're Will 2. All right.
Where's the head on the wolf?
I don't know. That's a good question. I thought that was it. Yeah, so maybe it did okay. The fact that it was able to capture the key properties and stick figures, it was pretty impressive. Okay. All right. So this one, it's our tendon profiles, right? Guess and check is one thing, right? Plot, allowable, tendon locations along the length of. And so that's a little bit different. So what we're going to do is kind of flip our equation around and solve for where we can put the tendons. And I'll show you. And you're doing the top two in your next homework that I'm going to assign today. Right? It's going to go through and you can go through and do that.
I don't like that.
What's that? You don't like that?
You're like concocted.
No, I know. I'm thinking. Was thinking of. Okay.
How do I make the homework on it?
No. We'll get it.
How do I copy Tim's homework?
See, so Tim maybe let you out early today, but then we wasted at least 10 minutes talking about about this stuff, right? So I was like, not wasted. You're right.
That might be on the exam.
What it might be, dude, is on the exam.
So, that wasn't wasting time at all.
Throwing that on like a dynamics exam, they have no.
No context.
What are these?
For extra credit in dynamics.
You get it?
Oh, I was saying you should just have the dynamics exam be our exam.
Or just really confuse them. I have had somebody accidentally be in my class before. They were supposed to be in a different class, and they came to my test for a final, and they took it. And I was like, how little did you go to the actual class to not realize that what you were taking a test on wasn't even related? No, I mean, I did great because they finally. I was like, dude, I'm sorry. They were like, you handed it, and I was just like, they had it completely blank, and I was just like, are you supposed to be here? And then they were not. No. Okay, so we're gonna do, like I said, we're gonna do these two. Tim did catch me in the process of making that quiz. Like he came to stop by. He said, "What are you doing?" And I said, "Nothing. Never mind. Don't mind. Keep moving." He also got me making some rap songs as well, which because I had chat make me some rap songs. I'll play those for you. A little bit. Educational, yeah. And so we're gonna do those two. The other one we'll touch on is this equivalent load method. I mentioned this before. We can trick a finite element analysis program into thinking it's doing, or we can trick it into doing, like post-tension and pre-tension design, right? It has no mechanism for dealing with internal, like the internal, the pre-stressing is causing internal moments, right? And we can trick the finite element analysis program into analyzing these by turning the effects that the internal pre-stressing forces do, we turn them into what an equivalent external force that does the same thing, right? So like the case where we had the drape, I could just put a distributed load pushing up on it, and that'll have the same effect as the draped. And then you analyze it that way. That gets done in PT floor design, and actually you don't have to do that by like the PT floor design will actually calculate that for you. But behind the scenes, it's doing this equivalent load method. Okay. There's also this. We are going to briefly look at this PCI design manual. This is available. This is on Canvas under one of the or what are they called? Modules. It's under one of the modules. It's the PCI design manual, right? And these are good for like the initial design. Preliminary design. Oop, very close. Right. And what they have in there is actually load tables. They have allowable load tables, right? But again, I think it's mainly just good for like the initial design, and then you'd have to go back and check all the stuff anyway. Okay, there's Mangel diagrams. We're not going to use those. Computer programs, right? Real World does this. I don't think anybody does Mangel anymore. Real World does that, right? And C-line method's just fun, okay? But that could also be used for design, right? You would have your allowable, where your C is at, and you would compare those to allowable locations, right? Is where your C is allowed to be and not be. Okay, so let's talk about each of these methods, right? The direct solve method, right? It's just using this equation, straight up using this equation. What gets a little bit complicated, right? You gotta be careful of signs. That's just a given. Just make sure you're really careful of your signs. The compression is going to be negative. Up is negative, down is positive, things like that. Okay. So this right here, FP, right? This is going to depend on the load stage. This is some more complexities that are floating around. Right? Am I using the one that has pre-stress losses, or am I using the one that doesn't have pre-stress losses? Right? EP changes along the length. Right? Or it could be constant, but it could change along the length. Along length of beam. Ooh. Right? And same thing with M external, right? This changes along the length of the beam too. Right? So you can see how, and then you'll have, I have written down F2, but really you're going to have an F1 and an F2, right? You might make that. So you're going to have a line for F1 and F2. Okay, like I said, with this method, what we do is for each load stage, you got to do this for each load stage because FP is changing and our allowables are changing as well. For each load stage, plot stresses at top and bottom along length of beam. Compare to allowable stresses for each load stage. If doesn't work, change things until it does. This is the guess and check part of it. I'll show you an example. Like I said, I think this is next plot right here I'm going to fast forward to is the homework solution, right? And so you could aim for it might be the homework solution. That's what I'll say. I think it is, but I'm not 100% positive. Part of it may or may not, just like the 9 may or may not be true. It might be 10.
It's
So
probably one off.
it's probably off at +1, right? So this is for a beam, okay? The beam that's from your homework. This is a tendon profile. We haven't got into that yet, but this has where you're allowed. My tendons have to be between these lines and these lines, right? Have to be in here, but we'll get into that one next. But then these are the stresses for the same beam under the same conditions, right? So this one right here is my initial load stage, right? Right at the transfer, right? And then F2 is the top of the beam and F1 is the bottom. So the red is the top and then the blue is the bottom. And you can see here, right, what should control in this case is it's going to be popping up, right? So my top, F2 is my top. So my top of my beam is right here, right? And it's getting close to the tension limit. These solid lines, the solid blue right here and the solid red down here, this is the tension limit state under initial conditions, and this is the compression limit state under initial conditions. And note, right, this value is positive because it's above 0, and this is negative, and so it's below 0. And so this is the compression limit is down here, and my tension limit is up here. And so you can see under initial conditions, you know, my top of my beam is getting close to the tension limit. My bottom of my beam is a long ways away from my compression limit. But you can imagine there are cases where this one right here could dip below this. And where you're going to be run into problems is if this went above this, right? And that means I violated that limit. So that worked out pretty well. And so you have to do it on different plots, right? Because this is under my initial loads case. This has to do, remember there was 2 different compression limits for sustained and total loads. That's what this one in the middle is for the sustained load because it has different compression limits, right? But this is under the total load. So this is my total service loads, right? Now what's up at the top that's getting close to the tension limit, what's up at the top that's getting close to the tension limit is the bottom, right? The bottom stresses are getting close to the limit up at the top, and then my compression limits are down here. So then I could run into compression up at the top under the service conditions, and this is tension down at the bottom under the service conditions, right? And again, if I go outside of everything has to stay within those 2 lines, right? And then the reason you plot across the entire length is because you got to make sure you don't violate things in between. Like if you have a straight tendon profile, then these stresses are these things right here. You could run into problems with these things. They would change shape, and you could run into problems near the ends. Like I mentioned before, right? You can see these things cross near the ends because those the external moments aren't there near the ends, right? There's 0 there, and so you flip it back around, and you can run into problems with tension up at the top. Doing that. Anyways, you'll play around with that. But then, and if you went through this and one of your lines crossed one of the lines, you're like, oh, that doesn't work. So then you have to go back, change your maybe number of pre-stressing strands or stress them more or something like that in order to make this work. Okay, and so that's the guess and check direct solve. So you're going to be doing that on the homework next week. And then this one is the second part of it, and we'll cover that on Monday. Okay, and then we have 1 minute, and I'll show you my rap songs. It is nuts. I don't know if I did this. So I've been incorporating ChatGPT into things more, just because I think you guys need to learn how to use it. Yeah, kind of.
Kirsten, that got an email from the
It was Flynn.
Okay, because a 205 student in the MLC also wasn't a fan because they had one at the end of their homework too.
Yeah.
And they're like, I don't use it. I like,
Some students think it's cheating,
like
but
it's
it.
like ChatGPT free. How do I talk to it? As a literally just type the question in and
Yeah.
it will give you the answer.
And that's the point. That's the point, right? That's the point, is to get people to do that.
It's only cheating if the professor tells you not to use it and you do use it.
Yeah.
And you get caught.
So I made one about lateral systems. That's probably most related to you.
Yeah, yo, we building.
I like this one better.
Yo, we building up high. Gotta keep it tight. Structure stand tall. Gotta do it right. Lateral lows try to take us down, but we hold strong, never touch the ground. Moment frames flex. Yeah, they move so clean.
Isn't this
Beam to
weird?
Columbus.
I mean,
That's the
ChatGPT makes the
scene,
lyrics,
no grace
and then this
spot.
program
Got
makes
open
the
space,
song.
but costs go up, man. What a case. We hold the
Isn't it
weight,
weird?
we take the strain. Moment,
It mispronounces Collins. It's called Cologne to rhyme, but
we keep it strong.
I made some country ones.
Brace frame steady, stiff as steel.
you could say what different version, like what style it's going to be. Ooh, I like this one. This is Dynamics.
Reincarnate with the chalk, like a king on a board. F equals MA, watch the motion get scored. Blue and gold in my veins.
Blue and gold in my veins, Bozeman in the sight. Like, what?
Mechanics, dynamics, this is how we take flight. From statics to the sequel, now the masses move.
Statics to the sequel. Dynamics to the sequel. Dr. Barry said some stuff. Look at this shit.
Isolate, choose axis. Check your units.
No,
tight,
I did it.
dimensional taxes. Position to velocity, then acceleration. Our text
So
is the
weird.
script. V is the narrative.
In the country.
Cowboy at 805. Sketching arrows on the page to keep it all alive. Process start simple, draw the free body clean. Sum of forces, F equals my, you know what I mean. Bridges in the window, snow on the emblem, chasing need a dot like a runaway friend. Moments round OEI and pen, country kid counting torque again. Under that big Montana sky, I find my way when I accelerate to write it down. At the work
Dude.
and energy, keeping my heart in time, like a fiddle.
I'm gonna be listening to these songs. Isn't that weird that they could do this? This is my playlist, dude. Yeah, play it during exams. Maybe the answers mixed in there somewhere, right?
That would be torture.
Listening to that. That's nuts that it does that. I mean, I'd be really worried if I was a country singer or a rapper or something like that. Like, that doesn't sound bad.